In today's lesson, we are going to look at the surface area of prisms and cylinders. So in the previous lesson, we looked at finding the volume. Today, we're going to be looking at the surface area. Now, in the volume, there was that kind of quick way of looking at the area of the base times the height. For surface area, there's not really as much of a quick way to do it. So unfortunately, we do kind of have to still just go through our kind of standard way. But we will talk about how we can kind of maybe make it a little bit easier so that we don't make as many mistakes. So, surface area of objects. So to calculate the surface area of a prism or cylinder, we must find the area of the base and top, either a rectangle, triangle, or circle, so similar to what we've seen in the past, and add the area of the sides, which generally tend to be rectangles. So a couple things you might want to do as you're going through this, right? Whenever you're given the diagram of a prism, ask yourself, how many surfaces are there? If you need to draw a net, do so to help you kind of organize your thinking and figure out that you have everything you need, right? So a net is basically an unfolded version of your prism. Think of every prism as a box or a container. If you unfold it and lay it flat, what does it look like? That's the net. You can also ask yourself, are any of the surfaces the same dimensions? So really, because you have to add up all the surfaces or the areas of all the surfaces, it might be easier as well to think, are there any surfaces that will have the same dimensions? Because if there are, we don't have to find the area multiple times. We can just multiply a singular area. So if I look at this shape, a rectangular prism, I'm going to break this down to look at it as a net. So if I break it down, we have these longer sides, right, which would be kind of what we see here. Then we have these shorter sides or shorter rectangles. We see one here. Then we'd have a longer side, a shorter side, so the far opposite side. And then we would have our base and our top. Now again, it doesn't really matter where they would go, generally speaking, assuming they go on either side. It just depends on how it would be orientated. So now that I have that, it might be helpful then to put in our measurements. So we know the tall vertical lines are going to be 20, these are going to be 12, and the small ones are going to be 6. Right? For our smaller rectangle down here, these would be 12 and these would be 6. So now we can go through and kind of figure out, okay, I've laid it out, I've drawn a net. Let's see if there are any figures or surfaces that are the same. Well, just from my drawing, even though it's not 100% accurate, I can still see that this surface is the same as this one. These two are the same. And these two are the same. So I have 2 of every surface. So I can just find the area of each one individually and then multiply that by 2. Or multiply them by 2. So the area of our first shape. And the nice thing is they're all rectangles. So that means length times width, or 20 times 12, which is equal to 240 centimeters squared. For the next area, length times width again, 20 times 6 equals 120 centimeters squared. Oops, that was area 1, that was area 2. Area 3 is equal to 12 times 6, which equals 72 centimeters squared. Now, this is for only one of those surfaces, but again, because we want all of them, we could do a shortened way where I add up all the surface areas and multiply them by 2. Could also say, well, I'm going to add up each one, or I'm going to multiply each one individually by 2 and then add them up. That's fine as well. So 2 times 72, keep it in order, 240 plus 120 plus 72. 2 times 432. And I get 864 centimeters squared. Again, because it is surface area, remember our units are going to be squared. Volume, they were always cubed. Surface area will be squared. So let's go through and look at some problems. A tent is in the shape of a triangular prism with a base that measures 4 feet by 7 feet and a height of 4 feet. How much material is needed to build the tent? Well, let's break it down into our specific shapes. We have our diagram here, right? So we could kind of draw in here. We know it's 4 feet by 7 feet, so 4 by 7. We know the height here is 4 feet as well. Are there any other measurements that we would need? Well, we would need this diagonal as well for this, imagine it goes up, this side. We won't need it for the bottom side because we already know that the base is 4 by 7, but this diagonal or the side panels, we're not quite sure what that measurement is. So that we're going to actually have to figure out. So how can I figure out what that measurement is? Well, we can use a little theorem that we may remember called Pythagorean theorem, or sum of squares. So the way this works, we do have our height, which is 4, but because we're only dealing with half of our triangle, the base isn't going to be 4, the base is going to be 2. So if we remember back to our formula, a squared plus b squared equals c squared. That's the sum of squares or Pythagorean theorem. A and b are the legs or the short sides. C is always going to be the longest side or the diagonal. So we have 4 squared plus 2 squared equals c squared. 16 plus 4 equals c squared. 20 equals c squared. So square root of 20 equals c. Don't forget that last step. We have to square root to get c. In this case, c equals 4.47. So that gives us now our diagonal of 4.47. Now I have enough pieces of information, right? Again, if it helps, feel free to sketch out your net. Right, I'm just going to roughly draw it out. Oops. So I've roughly drawn out my net here. I'm going to put in the information I know. We know that is 4. We know the base is 4. We know this is 7. We also know that this dimension is 4.47. So again, just some information to help us figure out our different panels. Now, if we want, we can go through and find if there's any panels that are the same. Well, I have one triangle here, one triangle here. Those are both the ends, so those are the same. I do have these 2 side panels that are the same as well. Then I have one panel in the middle, or the floor, that is its own figure. Now that I've recognized that, I can go through and find the individual areas. Base for the triangles, base times height divided by 2. 4 times 4 divided by 2 equals 4. Oh wait, no, my mistake. 4 times 4 is 16 divided by 2 is 8. My mistake. Feet squared. For the side panels, length times width, 7 times 4.47 gives us 31.29 square feet. And then lastly, for the floor, length times width, 7 times 4 is 28 feet squared. Now I can find the surface area. So the surface area is going to be 2 times the area of my base, or the triangle, or sorry, the area of the triangles, plus the area of the panels, because I have 2 of them. So all of that is to multiply by 2. And then I'm going to add in that floor panel. So 2 times 8 plus 31.29 plus 28. 2 times 39.29 plus 28. And in the end we get 106.58 feet squared. So that tells us how much material we need to build the tent, assuming we're just talking strictly material to make up the panels. We're not talking zippers and poles and things like that, like material or fabric. So that is the final surface area. So again, there's not really a quick way to do this like we talked about with the volume, or a generic way. We just have to break it down into a net, figure out what shapes we have, find the area of each, and then add them all up. Example 2. So tennis balls are packaged in a group of 3. One tennis ball has a diameter of 67 millimeters. How much material is needed for one cylindrical container? So we could look at this or break this down. We have our cylindrical container. Our container holds 3 tennis balls. And that's all the information we're given, other than the diameter is 67 millimeters. We know that they're groups of 3. So we do need some information here, because we need to know what is the dimensions, right? If I were to lay out this as a diagram, it would look something like this, right? The rectangular piece is the actual side. It does work out to a rectangle, and we have our 2 end pieces. So we do need to figure out what this information is, or the dimensions are. You can see that we have 2, again, like I said, 2 of the circles, 1 of the rectangles, but we still need dimensions. And that's where that piece of the 67 millimeters is going to come into play, because that's the diameter. So that is actually the distance across our circle. So that helps us figure out one of 2 things. One, it helps us figure out how wide our cylinder is, or the diameter of our circles. It also, because the diameter goes in both ways for a sphere or a circle in this case, looking at 2 dimensions, it can actually give us the height as well. So the height in this case is going to be 201 millimeters, which is 67 times 3. So 67 times 3 is 201. That gives us the height. That also lets us add in a dimension, the height of this rectangle. We now need to figure out what is the length of the rectangle. Right, I have enough information to help me figure out for the circle, because I know the radius is 67 divided by 2, which is 33.5. But what is this horizontal distance of my rectangle? Well, if we think about it, the rectangle, it curves all the way around our circle, or that is how long it is. So that is actually the circumference. So the circumference of our circle, with a diameter of 67, is the length of this rectangle. So circumference is equal to pi times diameter, or 2 pi r, but because we're given the diameter, we might as well use it. So 3.14 times 67, we get roughly 210.38 millimeters. So that means that our length of our rectangle is 210. Now we have enough information to go through and find the area of each figure. Area of a circle is pi r squared, so we have 3.14 times 33.5 squared, which works out to 3,523.86 millimeters squared. For the rectangle, length times width, so 201 times 210.38, which gives us 42,286.3 millimeters squared. And then to find the total area or surface area, because I have two circles, I'm going to do 2 multiplied by that area and then add in the area of the rectangle. So 2 times 3,523.86 plus 42,286.3, and then we end up with 49,334.02 millimeters squared. So that is our surface area. So that is part 1. We now know how much material is needed for one cylindrical container. Part 2 now says, for shipping purposes, tennis balls are shipped in packages of 6 cans, as we can see in this figure here. How much cardboard is required to form a box that contains all 6 ball cans, or tennis ball cans? Well, let's draw out a rough sketch of our box. We know it has to fit 6 cans in here. We know the height is going to be 201. So regardless of how we look at it, it's going to be 201. Because it's labeled 3 across, if we imagine we have 2 cylinders going this way, then we have 3 going down the other way, if you imagine that with our drawings, we can figure out what the width is, because the width has to be 2 diameters long. So in this case, 2 times 67 was 134. For the length of our box, it's going to be 3 diameters long. So 3 times 67, which gives us 201. So now we have enough information to figure out what our box is going to be, or our surface area. So again, it might help to just quickly break down our box. We're going to have 4 and then 2. The 2 on the ends are going to be 134 times 201, and it works out that all of the panels, or the side panels or the long panels, are all going to work out to be the same measurement or area, because it's 201 by 201. So we have 2 boxes that have on the ends, and then we have 4 panels that are all the same. So if we find the area of our end pieces, length times width, 201 times 134, we get 26,934 millimeters squared. For our 4 side pieces, length times width, 201 times 201, 400 or 40,401 millimeters squared. And then finally, for the surface area in total, I'm going to take 4 times area 2 plus 2 times the area 1, right, based on how many sides or surfaces that are the same. So 4 times 4 times the 40,000. Oh wait, no. I think I may have made a mistake here. Found the correct areas. Now, do I have enough of the same ones? So measurement's the same. That's the same. So it's actually switched around. I have 2 of the other areas. So it actually works out, because it's the height that's the same as the width, that it works out that 2 panels are the same as well. It's just the side panels that are separate. So our individual areas are fine. So when we go down to this final formula here, it's actually 4 times area 1 plus 2 times area 2. So 4 times 26,934 plus 2 times 40,401. And in the end, we get 188,538 millimeters squared. So again, that's where it can be very helpful to draw out your net and label your dimensions, so that you make sure you understand how many of each surface area you have. Moving on to the last question. A bearing is being made for an automobile part as shown below. How much steel is required to make the part? Then we have to think about how much spray is required to coat all outside surfaces of the part. And then we're given the cost for stainless steel and regular steel, and then a cost for a rust-resistant coating, and we want to figure out then the cheapest way to make the part. Let's start with piece by piece. How much steel is required to make the part? So when we're asked for how much steel, this is actually volume. So we're actually combining 2 things here. So we actually have to find the volume. So in order to find the volume, we could do one of 2 things. We could find the area of the base, which is this composite figure of a circle minus another circle. Or we could find the volume of the entire figure and then subtract the volume of the missing piece. So we can find the volume of the entire cylinder, assuming that it's filled in, find the volume of the center, and subtract the 2. So let's go that way. Let's find the volume of each piece and then subtract them to find the total volume. So we're going to label this outside part, or the entire part, 1. This inside part will be 2. Actually, let's keep it color-coded. So the volume of the first one, pi r squared h. So pi times r squared. So the radius is half this diameter. So the radius is 12. So 12 squared times the height, which is 38. Works out to pi times 144 times 38, which is 17,190.79 centimeters cubed. For the second volume, volume 2, again, because it's still a cylinder, pi r squared h. Here the radius is 5, or half of 10. So pi times 5 squared times 38, or pi times 25 times 38. Remember to do that exponent first. Get 2,984.5 centimeters cubed. And the total volume is going to equal the overall volume minus the cylinder that's missing, 17,190.79 minus 2,984.5, and left then 14,206.28 centimeters cubed. So that is the total volume. So that is how much steel is required. Now we need to figure out what is the cost for this, or how much spray is required to coat the outside surface, and then figure out the cost. So to figure out the rust resistant coating for all outside surfaces, we need to figure out the surface area. So because it is for the outside surface, we don't need to worry about the inside surface or that inner cylinder. It's just everything on the outside. So if we look at the figure, everything that's shaded in gray. So that means we have to find the area of the two end pieces and then the rectangular, or the side, the rectangular piece or surface that goes around. So let's just do a cross section of the base, or the top and the bottom. So we know we have a large circle, and then we're missing an inner circle. The entire dimensions or diameter is 24. So I need to find the area of a circle with a specific diameter, essentially. So what we can do is area equaling pi r squared. We can actually do area is pi times r squared, or r1 squared minus r2 squared. So one radius subtracting the other. So in this case, pi is equal to 12 squared minus 5 squared. Pi is equal to 144 minus 25. And we get 373.8 centimeters squared. I now need to multiply this by the rectangular surface, or add it, to the rectangular surface. The rectangular surface again goes all the way around. So that means the width, we know the height is 38. The width is our circumference, because it goes all the way around the circle. So in this case, do a small side calculation. C equals pi times diameter. In this case, we just use the overall diameter. So pi times 24, which works out to 75.4 centimeters. So that gives us the width, or the length, you could say, whatever you want to argue. Then finally, we can now find the area. Area equals length times width. So 75.4 times 38, 2,865.2. And then to find at the very end our surface area, it would be 2 times 373.8 for the two circular pieces, plus 2,865.2 for our rectangular piece, to give us a final surface area of 3,612.8 centimeters squared. Now we need to look at the cost. So if I want to find the cost, the stainless steel itself costs, or stainless steel costs $0.06 per centimeter squared. Regular steel costs 0.04 per centimeter squared. but all the surfaces must be covered with the rust-resistant coating. So we're going to have to add the rust-resistant coating either way. Looking just at the cost itself, because we're making it out of steel, we can see right off the bat that regular steel is going to be the better option. So let me actually move this over. So regular steel is going to be the better cost. So if we look at the regular steel, $0.04 multiplied by the volume, so 14,206.28. This gives us a cost of $528.25. We then have to take the surface area, 3,612.8, multiplied that by 0.02 for the rust resistant coating. It's $72.26. And then the total is just adding them together. So 528.25 plus 72.26, 640.51. So that is the final cost. So just highlight a couple of our measurements and our final answers, just to make it easier to find. So quite a long question, but again, work through it. We need to identify things, draw it out as a net if needed to then help us figure out the surfaces that we're dealing with. We can break that down and use the general formulas that we know. Looking at the formula sheet, it might give us a little bit more a singular formula rather than breaking it down, like say for the circumference and then multiplying and then finding the area of the rectangle. So it might combine all of that to make it a little bit easier, or you can work through it surface by surface, piece by piece, like we've done here. Right? But again, remember that just surface area is the area of all the surfaces added up.